This lecture, part 1 of 4, will cover the chemical level of organization in the human body and provide a chemical foundation for the course. Starting a course devoted to the study of human anatomy and physiology with chemistry may not be expected. However, chemistry plays a vital role in the human body. Chemistry is defined as the science that investigates matter and its interactions. Understanding the body at the chemical level is important. By recognizing how the atoms and molecules that compose the body behave and interact, a better understanding of the body's cells, tissues, organs, and organ systems can be obtained. To help gain an understanding of this lecture segment will review some basic chemical terms and concepts, including the topics of atoms, molecules, compounds, and chemical bonding. As defined earlier, chemistry is the science that investigates matter and its interactions. Matter refers to anything that takes up space and has mass. Matter is composed of elements, which in turn are composed of atoms. Elements are substances that cannot be changed or made simpler. They are the simplest form of a substance. Examples of elements include carbon, sodium, oxygen, as well as many others found on the periodic table of elements. Atoms are the smallest stable unit of matter and contain 3 major subatomic particles, known as protons, neutrons, and electrons. Both protons and neutrons are found in the nucleus of the atom. Protons carry a positive charge, think P for positive, and neutrons carry no charge and are known as neutral, hence their name. Electrons, on the other hand, carry a negative charge and orbit the nucleus in what are known as orbital clouds, often represented by an electron shell, as in the diagram below. Let's take a closer look at this diagram for review. Here we have an atom of the element helium. Helium is composed of 2 protons and 2 neutrons in the nucleus, shown here. Here we see the positive protons and the neutral neutrons found in the nucleus of that helium atom. Helium's 2 electrons orbit the nucleus in the electron cloud, represented as an electron shell seen here. So here we have that electron shell and the 2 electrons that are orbiting the nucleus of the helium atom. There are several terms used to give information on the composition of atoms. Atomic number refers to the number of protons found in an atom. Each element has a unique atomic number. For example, the atomic number of carbon is 6. This means that all atoms of carbons will have 6 protons in their nucleus. In addition, in an electrically neutral atom, the number of protons will equal the number of electrons. While all atoms of elements will have the same number of protons, the number of neutrons found in the nucleus can vary. These atoms, with the same number of protons but different number of neutrons, are known as isotopes. Isotopes will have different atomic mass numbers. Atomic mass number is defined as the sum of the number of protons and the number of neutrons found in an atom. Some isotopes may be radioactive and emit radiation and/or subatomic particles as their nuclei spontaneously break down. The atomic weight takes into account all of the isotopes of an element and their relative abundance to provide an average mass. The diagram on the right demonstrates the information that can be found on a periodic table of elements for each individual element. In this case, we're looking at carbon. The large letter in the center of the square is the chemical symbol for this element, shown here. We will also find the full name of the element, as well as its atomic number, again what tells us the number of protons in the nucleus of this atom, and also we will find its weight in grams per mole, that atomic weight here in the upper right hand corner. So to review, we have atomic number, which is going to be equal to the total number of protons that we find in the nucleus of an atom. Isotopes, they're going to have the same number of protons but different number of neutrons. The atomic mass number can distinguish isotopes because atomic mass number is equal to the number of protons plus the number of neutrons. And atomic weight again is going to be that average mass of that element. This table here represents some of the common elements that we find in the human body. For each element, the symbol is given as well as a brief summary of its role in the body. Many of these elements will be discussed throughout the course. For now, it is a good idea to become familiar with these elements and their symbols. So briefly going through the table, we are going to find a lot of oxygen in the body. Oxygen's chemical symbol is O. We also have carbon, the symbol being C, hydrogen with the symbol H, nitrogen has the symbol N, calcium, the symbol Ca, phosphorus, the symbol P, potassium, the symbol K, sodium's chemical symbol is Na, chlorine, Cl, magnesium, Mg, sulfur, S, iron, Fe, and iodine, I. As mentioned earlier, atoms are electrically neutral, and this neutrality is achieved by balancing the number of protons with the number of electrons. In the case of carbon, there are 6 protons in the nucleus, giving a total charge of 6+, and 6 electrons orbiting the nucleus, giving a total charge in the electron cloud of 6-. This results in a net charge of 0 for the atom, which is obtained by summing that +6 charge against the -6 charge, bringing it to 0. The electrons orbit the nucleus in what are known as shells. Electrons will fill their inner shells first, and each shell has a finite number of electrons it can hold. For example, the first shell can hold 2 electrons, the second shell can hold 8, and the third shell can hold 8. The electrons found in the outer shell of an atom can interact with other atoms and are known as valence electrons. Depending on how many electrons are found in the outer shells, the chemical properties of the atom will vary. Atoms like to have a full outer shell because it is stable, and they will react to achieve this as possible. Things always like to achieve a stable state if they can. Let's examine the difference between an atom of carbon and an atom of neon. Carbon has 4 valence electrons in its outer shell. Those valence electrons or outer electrons can be seen here. 1, 2, 3, 4. 4 electrons in its outer shell. Neon, on the other hand, if we take a look at its outer orbital shell here, we see there are 1, 2, 3, 4, 5, 6, 7, 8. So the outer shell, the second shell, this would be shell number 1, shell number 2, has 8 electrons, which is the maximum capacity the second orbital shell can hold. So neon has a full outer shell. Recall that atoms like to have a full outer shell because it makes them stable. Since neon has a full outer shell with its 8 valence electrons, it is considered a stable element, in fact a noble gas, and it will be non-reactive. Carbon, on the other hand, does not have a full outer valence shell. It will be reactive in order to try and achieve that more stable full outer shell. So carbon will be looking to either get rid of 4 electrons or gain 4 electrons around its orbital to obtain that stable configuration. Atoms will often react with other atoms and form what are known as chemical bonds. Chemical bonds hold the atom together after the chemical reaction has taken place and are formed by the sharing, gaining, or losing of valence electrons, or outer electrons, the outer electrons in those outer orbital shells. The term molecule refers to having more than one atom bonded together. An example of a molecule would be oxygen gas, denoted O2. And the term compound refers to when 2 or more elements are bonded together. An example of a compound would be considered carbon dioxide. Here we see we have the element carbon as well as the element oxygen, and they are bonded together. There are several ways atoms can bond together. First, ionic bonding will be examined. To understand ionic bonding, the terms anion and cation must be defined. An anion is an atom that gains electrons and becomes negatively charged. A cation is an atom that loses electrons and becomes positively charged. Whether an atom will gain or lose electrons depends on the number of electrons in its outer shell, or valence shell. Remember that when an atom wants to achieve a stable state by having a full outer shell, it will do this based on what is easier to accomplish. If it is easier for the atom to give away electrons it will, or if it's easier for the atom to gain electrons to achieve that full outer shell, it will go that route. Ionic bonding occurs when a cation and anion are electrically attracted to each other, and this attraction is what results in the formation of an ionic compound. Let's take a look at how this works. In this instance, a neutral sodium and a neutral chlorine atom are being considered. Recall that the reactivity of each atom will be affected by the number of electrons found in its outer shell. In the case of sodium, there is one electron in its outer shell. Sodium has two options to achieve a full outer shell. It can lose the one electron that is already there, or it can gain 7. It is much easier for the sodium atom to lose one electron than it would be to gain 7. The reverse is true in the case of the chlorine atom. Chlorine already has 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7. It only needs to gain one more to reach 8 and fill its outer shell, which is much easier to do than to have to try and lose 7. So chlorine would rather just fill the one spot it has rather than taking the energy and the time to try and go ahead and get rid of all of those other 7 electrons in its outer shell. As a result, sodium will therefore donate its outer valence electron to chlorine. So sodium is going to take its one extra that it wants to give up, and it's going to give it to the chlorine, which is looking to gain one. As a result, from giving up one of the electrons, sodium will take on a positive charge and become a cation. You can think cations have that plus with that T in the middle, so you can know that they are the positive charged ion. And chlorine gained this extra electron, the one that sodium gave it, so as a result it's carrying one more than usual when it's neutral, and it will take on that negative charge and become an anion. When chlorine becomes an ion, its name changes to chloride, and this is known as a chloride ion. So, now that we have our cation and anion that have formed, the electrical attraction between the positive charge of the cation and the negative charge of the anion will attract these two atoms together, forming an ionic compound, in this case, sodium chloride. Rather than donating or accepting electrons and becoming ions, some atoms bond by sharing outer electrons in a process known as covalent bonding. Consider two hydrogen atoms. Each has a single outer electron in its first shell. Recall that 2 electrons will fill the first electron shell, so each hydrogen would like to gain an electron. When the hydrogen atoms share their outer electrons, it results in both hydrogens having a full electron shell. The sharing of this pair of electrons results in a single covalent bond. So taking a look at that, we have a hydrogen atom with 1 electron in its outer shell, and another hydrogen atom with that single electron in its orbital shell. Since this is the first electron shell, it will want to fill with 2 electrons. As a result, this hydrogen atom can go ahead and share its electron with the other, and vice versa. This results in the sharing of that electron pair and that single covalent bond forming. Double covalent bonds can also form when the bonding atoms share 2 pairs of electrons. This is demonstrated by the covalent bonding of 2 oxygen molecules. Each has 6 electrons in its outer shell, meaning they need 2 additional electrons to achieve the full shell in a stable state. This is accomplished by sharing 2 electron pairs between the atoms and results in a double covalent bond. So to get started, oxygen is going to have 1, 2, 3, 4, 5, 6 electrons in its outer shell. We see in the darker orange color here the 6 that come from the other oxygen molecule, 1, 2, 3, 4, 5, 6. So what will happen is this oxygen molecule will go ahead and share 2 of its outer electrons with the other, and the other will go ahead and share 2 of its electrons with the original oxygen molecule, so 2 pair. And as a result, the sharing of these 2 pair of electrons will result in what we know as a double covalent bond. The sharing of electrons between atoms makes covalent bonding relatively stable and strong. It's important to note too, you can have more than one type of atom forming covalent bonds with another. Here we have an oxygen double bonded to a carbon, and a carbon double bonded to another oxygen. Both of these would be examples of those covalent double bonds. When atoms share electrons, they are not always shared equally. Some atoms are more electronegative, meaning that they will hold on to the shared electrons more than the other atoms. They have a greater affinity for them. Let's examine the water molecule below. The oxygen atom will want to hold the electrons near itself more than the hydrogen atom will. This causes a slight negative charge to form by the oxygen and a slight positive charge to form on the end of the where the hydrogens are located, resulting in what is known as a polar molecule. A polar molecule is a molecule where there is a slightly negative and a slightly positive end. In this case, the covalent bond formed by the sharing of the electrons is known as a polar covalent bond. If the electrons are shared between the atoms, no partial charges will form and the bond is known as a nonpolar covalent bond. So in the case of water, if we take a look at a water molecule, what this is saying is that the oxygen is going to hold the electrons that are being shared between the hydrogen and the oxygen forming this covalent bond a little bit closer to it by its orbitals, resulting in a partial negative charge in this area. And a partial positive charge will then form by where each of the hydrogens are. And as a result, we're going to go ahead and have an area which is a little more negative by the oxygen end and an area that's a little more positive by those hydrogens. And that makes these bonds right here those polar covalent bonds. When polar covalent bonds are present, there can be a weak attractive force between the molecules. This weak attraction is known as hydrogen bonding. It is important to understand that hydrogen bonds are just weak interactions between molecules. They do not actually create molecules of their own, but they can pull molecules together and alter their shapes. Hydrogen bonding is displayed by water, and it is this weak interaction that accounts for the phenomenon known as surface tension. So here we have a diagram depicting all of our different water molecules throughout here. We'll go ahead and see by that oxygen we have that partial negative charge there, and by the hydrogens we're going to have this partial positive charge here. And what that does is it forms that weak interaction denoted by these red dashes here. This isn't a true bond. We're not going to take this water molecule and bond it to this water molecule, but there is enough attraction there to create that weak force, and that's what we call those hydrogen bonds. Before moving on, let's take a moment to review some key terms. Feel free to pause the lecture to form your own response before moving on. Try to define the term atom in your own words. Atom is defined as the smallest stable unit of matter. Let's go ahead and try one more question. Define chemical bond and identify several types of chemical bonds. A chemical bond is the attractive force between two atoms that holds them together. Two examples of chemical bonding that we explored were ionic bonding, the creation of bonds by electrical attraction between an anion and a cation, and covalent bonding, created by the sharing of electrons between atoms.